Hello everyone, and thank you for joining us today. My name is Lo, an optical application engineer of Cybernet System Malaysia. So I'm very excited to welcome you to this webinar where we will introduce you the optical design software, which is the Ansys Zemax OpticStudio. So as the title show here, we will discuss about design and optimize the optics system with this Zemax OpticStudio. So today's agenda, we will go through about the Cybernet group and the about company information. And next, I will show the demonstration on the optical design and the optimization in OpticStudio. So later I will switch the screen from the PPT slide to the software. So lastly, I will introduce or discuss the Zemax products. Okay. So here, let's start with the introduction about us. So as you see, this map is the pinpoint for the Cybernet group for the global network. So for here, Cybernet Malaysia is a subsidiary fully owned by Cybernet System Company Limited, headquartered in Tokyo, Japan, and we established about 38 years ago since 1985. So Cybernet's partnership with the Ansys also have a long history. So another two subsidiary, we have two subsidiary in China and Taiwan. So in Europe and also the North America, we have a Symmetric, Microsoft, and Neosys solution. So these three company is our sister company. Also is a part of the Cybernet group. So next we will go to the service. So Cybernet Malaysia support customer in the Asian region. So we will cover the Southeast Asia region and the country. So we are the channel partner of Ansys in Southeast Asia country. So Cybernet System specialize in computer age engineering solution. And we also provide the engineering service, training, and also the consultation about the software in those domain. So later we'll show the domain from the Ansys software link. So, but today we will focus more on the optics, which is the optic analysis, the lens design, and also the learning plan. As you see here, we will provide the learning pack, the solution, the teaching plan for the beginner for this software user, so they can pick up their skill faster compared to maybe on learning to read the user manual or self learning. So next, this is the Ansys Multiphysic Platform. As we see on this slide, Ansys Multiphysic Platform consists of the structure, fluid, electronic, semicon, and 3D design. So in the past 3 years, the new multiphysics that add on is the optical and the photonic. So the software we include inside this optical is the Sphere and also Zemax OpticStudio. So for the photonic, we have a numerical. But today we will focus only on the optical software, which is the OpticStudio. So, Ansys optical and photonic aspect provide the holistic solution for the optical design and simulation. So the optical design we can do from the structure size, which is in the numerical here, up to the system level, which is the Sphere. So in the middle, we have the Zemax for the optical component modeling, which is the lens and also optomechanical design. Okay, so the introduction about our company and also we have the Ansys partner and the business we have. So let's go with the demonstration. But before the demonstration, I will show some information to let you know what is the design I'm going to show later. So here is the design I will show later. So the double gauge lens design and optimize. So the design will be start on this, which is a single field and a set of lens and is non-focus on the image plane. So after that, we optimize and we add on the three field here. And here is a focus design, which is the optimized design. And lastly, I also going to use this design to demonstrate how to analyze the stray light in this system. So before I start, I will discuss the design specification. So the design specification, the F number is 3 and 75 mm focus length. And we said this is the wavelength, red, blue, and green. So the design for 35 mm film, which is 24 by 36 format, and the image height is 21.6. So 21.6 is the diagonal here. Here we can get about 43.2. So the radius of this circle is about 21.6. And we want to make the distortion less than 1%. And also we add in the 2 H for the lens, so we can make it assemble to the mechanical casing. So lastly is the back focus distance. So we need at least about 40 mm for the mirror clearance. Okay, so now I will switch to the OpticStudio. Okay, so now this is my screen. So I will show you the initialize design. Okay, here is the initialize design as I show inside the slide. So now we want to set up the configuration for this lens like just now. So we go to this field. So as just now, we want to have a field point about 21.6 mm. So we have a field wizard and we use a parallel image height. Now we set the equal area for the Y field and we set the height is 21.6 mm and we apply it. So we will see there is three fields, one from the center, which is on axis, and two is from the off axis. Okay, now we close it. After that, we add on the setting, which is the visible light, the red, blue, and green. So we set this. So now we have three frequency here. As shown here, we have three frequency. Now we also close this wavelength. So now this is our design. So we can see all the ray is unfocused on the image plane. So we can use some analysis tools like this. let's show the image on the plane first. Okay, as you see here, now the image is unfocused on the plane, and the original image will be okay. Here is a source bitmap compared to the image. Here is the object. Here is the image side. Object side on the left, image side on the right. So, okay, before we do the optimization, we still need to add on the, just now we mentioned the 2 mm clearance for the top and the bottom. But here the chip zoom, we just add 1, so they can add top and bottom at the same time. So we only add all the surface with 1 mm, but object stock and the image, we never add 1 mm. Okay, so image stock, we never add 1 mm. So based on here, we will use the MTF optimization. So before we make the optimization, we set the response of the film using 50 cycle per mm. Okay, as you see now, the sampling now is inaccurate and also is non-focused. So later on, when we, after the optimization, the output will be different. So the things will be focused on the image from the source. So small out first, and now we use a quick focus. Okay, before we make the optimization, we can use a quick focus to optimize the design if the quick focus can make this, but somehow the quick focus cannot optimize this design. So we might use this merit function. So for the setup merit function, we use the contrast image quality, so we can make the image more focused, but we want the response, which is the spatial frequency at 50. So the weight for the SNT is 1 and 1. The maximum distortion is 1%. And we set this pupil integration 4-ring and 6-arm. And here we set the boundary. When we optimization, we don't want the lens thickness too big or too small. So we can set the thickness here for the boundary of the glass and also the air. So for now, we set the glass minimum is 2, maximum is 12, and the edge thickness is 2. And the air gap, we set 0.5 mm. And the edge, we also set to 0.5. Okay, so here is the setting for us to apply here. Apply here. So the wizard will auto generate the required information for the variable we want to optimize. Okay, so beside here, okay, let me open the optimization file. So beside here, we also need to add on this CTGT, which is just now we say the back focus 40 mm. So here is CTGT is greater for the surface 11. We need to greater than 40 mm. So which is the last surface here. Now it's 75.4. So we need to make it greater than 40 after the optimization. So next is the checker. We want to check the on axis and the off axis. So we set the response of the firm and what is the target percentage we want to see on the output. So for here, because we are monitoring using this wizard, so we never set the weight to 1, just let the weight is 0. So for here, the important note, if the percentage here less than 20%, then our eyes can differentiate the contrast between the source image and also the output image. So after we set these optimization rules, so now we need to go to the lens editor. We need to change all this radius and thickness into a variable before we make the optimization. Okay. So we can highlight all this and using a Ctrl+Z to make it as a variable. Or you can select here and change it into variable. Also here. So after we change it to a variable, then we can use the optimization tools. Okay, better I show the photo. I show this blur photo and also the blur photo and also this MTF. Okay. Now we will start the optimization. So after the optimization, we will get the result better than the initial. All right, here is the optimization will be n. So we optimize 20 variable. We use the damn least square. Here we have two kind of algorithm. Normally we will use for the sequential design, we were using the damn least square. And the non-sequential design, normally we will use the orthogonal designs. So now we exit this wizard. So as we see the optimization, so we make the things, the response better, means the contrast here is about more than 50%. So I can show here. Just now I mentioned, so the value here, we want to monitor. So it's a quite good result, which is better than our target for this top 3. We greater than our target. Just 1 is smaller than our target. So we can, because the off axis, somehow we will not easily compared to the center field optimization. So we will reduce the target for off axis compared to the on axis. So if I figure the image here, okay, you can see there is some distortion and the curve field is not perfect optimization. So we need the further optimization for this design if we want a better result. So another thing is the distortion. So if I change the photo into a line, then we will see the line is not a perfect line. So there is some distortion on this design. So we need the further optimization. But today I'm not going to show the further optimization for this design. So for now is a well demo on this optimization design. So next I will use this design to show the straight line analysis. So first of this, we want to change this design to the non-sequential design. So before we change, we need to make the design lockdown. Okay, we save into another file for production maybe. Okay, so we save a new file, and now we log the number of ray for the tracing before we convert it into the non-sequential. Okay, now we can go to the File tab and go to this Convert to Non-Sequential Component Group. Okay, we save it. And now we convert to non-sequential. So we save a file into the Pro non-sequential. So now you will see the design in non-sequential mode. Let me show the 3D diagram. So you can see there is three field because we said three field. So convert to the non-sequential, we have three source. And because the image just now in the sequential mode, we have one image plane. But now when we change to non-sequential, so we have three detector here. Okay. So for now, we want to see the straight line analysis. So we add another object, which is the color detector. Okay, the color detector. So I want to analyze the full field to see the straight line occur on the image plane. And now I'm going to refer the object to object 13 to align my position. Okay. And I will set my dimension. Okay, the dimension is here. The half width dimension we set to 50. So the entire size will be 100 by 100 mm. And the pixels we want to show on the detector, we set it 150 grid between the y-axis and also the x-axis. Okay, so it's a perfect square analysis. Now we can see the image plane here. So because we want to analyze the straight line, so we're going to change the analysis light rate lower for the faster simulation result. If we set the analysis rate more, then our ray tracing will take more time. So, and we need to go to System Explorer. Okay, because we want to do the straight line analysis. So we need to add this maximum intersection per ray and also the segment. So if we set this number higher, so we can analyze more reflector ray and also the ray split in others direction. So for now, we set to 4,000 for the intersection, and we set to 2 million for the ray segment. So after this, we can show this. We take this, split the non-sequential ray, and the system will auto click the polarization. So here is the straight line happen internally inside the system. So now I'm going to make a ray trace to check the result. So we need to take this split NSC ray and also using polarization. So now we clear the and trace it. Okay, now we done. So we can use the detector view to show the result for the full field. So just now we said the color is full field. This is set to full color. Okay, here is the straight line. The 3 point is the image focus point, and the remaining the blue snow shape, blue color sky is the straight line. So for now, we will analyze this straight line. So one of the step, we can using the filter. So we using the G0, which is the ghost light. And we use the ampersand. And also we want it hit on object 11, object 17. So which is the detector here. So now you can see the light ray in this way. So we still see a lot of light ray, the straight light. So if we want to analyze the strong straight light from this system without consider the weak straight light, so we can change this configuration, minimal relative rate. So here is the 1 micro from the original power. So maybe we can set the minimum is 0.025. So now we can analyze the stronger ray in the system. Instead, we analyze the entire, the strong and also the weak. So when we make this refresh, then we can see where is the light ray go. Okay, so this feature only the pro version user can use, only can use this method. But if you are the premium user, okay, premium user, you can use the path analysis tools. But before we make this analysis, let me reduce this straight line in the image plane. So we want to reduce some of the portion. Okay, so now we go to maybe object 6. We add the coating on maybe the back surface, and we add the AR coating, which is anti-reflection. And also we add one more maybe on 12, object 12. So we add the front face, the entrance, and we make the AR, anti-reflection. So now we using the ray trace again, and we now save the ray information. It's done. So now we open back the detector. Okay, so as we can see, it's largely reduce the straight light on the system. So we only the higher energy on here, okay, and also on here. So how we going to analyze this? So we will use the path analysis tools. The comparison here is when we use the 3D model. The 3D model here, we can only see the light ray from the source go to which object and hit on this detector. But in the path analysis tools, we will see the object actually have how many branch, and also there are from object 3, start from 4, go to 5, 6. At the end, they will go to the image plane, which is the detector at the 17 object. So now I will going to filter this analysis data, which is the ray file I saved just now. So to analyze this portion or this portion, So now I will using the code here. So we want to analyze the ray from the object greater than object 17. So we set greater than -14. Okay. The position is here. We set -14 and a +14 and -50 up to maybe -43 for this region. Okay. So less than object 17 and positive, and the y-axis we make it greater than object 50, and the x y lt, okay, less than, using the maybe -47. Okay, now we see reduce the light ray on the particular region we want. Okay, so we can copy this code and we can put in the 3D, and we use the database just now. Okay, so now we can see the entire ray, the stronger straight line ray, after we filter from the ray base. So we also can check in this way. See, it's exactly same as this position. On this position, we want to analyze. So of course, we also can analyze the wave in one. So maybe I want to analyze the first ray, the path. So I use ampersand underscore, 1 is the first ray, 2 is the second ray. So we will see the ray in this way. This is 1 from the object 3, go to this object 4, and direct go to this object 17. So of course, we also can change to 2. Okay, then now we can see is from the object 3, go to which object. So it is similar to the path analysis tools. We also can using the same way to analyze the result. Then you will see which is the direction it go. So we can analyze what is the flux on that particular portion. So in the perfect way, we add on all the anti-reflection on each surface, so we can greatly reduce all this straight light. Okay. So here is the demonstration. I will do it up to here. So next, I will continue back to my PPT. Okay. So just now I demonstrate the usage with tools, and also the without tools is a comparison. So without the tools, we need to use maybe hand calculation. And if we want to do the optimization multiple times, maybe difficult because we need to recalculate every time, and it consumes a lot of time on the optics design. And otherwise, we need to have a cost to do the prototyping and testing. And also we difficult to illustrate to someone, because just now I also demonstrate the straight line. Maybe without the tools, we are difficult to understand or illustrate where is the straight line and where is the right light ray go. So with tools, we use the ray tracing calculation, and we easy to optimize and reduce the time design. And also inside the software, we consider a complete workflow from design, analyze, optimize, and tolerancing the design before we making a production. So after that, this will reduce the cost for the prototyping, testing, and also we can easier to illustrate the design and also the 3D for others. So next, I will go to the Zemax product. So here, Zemax is a leader in the optical product development software and is trusted by engineers worldwide. So the Zemax capability to simulate the imaging and also the laser and fiber, which is in sequential mode, and the lighting and illumination is the non-sequential mode, so which is the all-in-one design in one software. And also we have the Zemax tools, the package, or we call the Zemax switch. So we can consider there is a set of tools that can, for the design, simple. So as we see, this is a lens. So we have optic design, the mechanical casing design, and also we have an electronic design here. So our capability is we have all these, the tools can make the engineering work together and manufacture reliably to achieve the design performance within the design for the simulation, the environment. So what is the technology does in this Zemax? So basically the Zemax is the ray tracing. Ray tracing is the core technology for this software. So it is a state-of-the-art software package for optical imaging, illumination, and the optomechanical design and analysis. So the Zemax software help company get a qualified design more quickly by streamlining the workflow and communication between the optical, mechanical, and manufacturing engineering. So here is the workflow. We start with design. So maybe we have a lens set for the radius and also the surface type and also the thickness. So we make in the lens data editor. After that, we use the analysis tools like just now. We can analyze before we make the optimization. So after that, we can optimize the design by using the wizard. Just key in the requirement or the design specification inside the tools. Of course, we have a graphical design, the GUI. Then we can make the non-engineering person easier to understand. So engineering maybe can refer to the technical analysis tools. After we optimize, we will maybe go back to analyze again, check whether it meet the specification. So before we want to make the manufacturing, so we will go to the tolerance. We set the tolerance and the offset if the system go manufacturing error or offset. Is there any effect on the output? So lastly is the connect with the macro. We have a coding. Then we can use this macro, the ZOS API, to optimize the design. If the analysis is regularly or repeatedly, then we can use a macro to run it automatically. So here is the product suite we have. The OpticStudio mainly we use for design, analyze, tolerance the optical component. So the OpticStudio Star module is the add-on to the OpticStudio for enterprise license. So the main analysis here is we analyze the impact of the structural and also the thermal load on the optics design. And lastly is the optic builder. This is the add-on for the cryoparametric platform. So we use this add-on into the cryoparametric platform design, and we can export the ray from OpticStudio to Optic Builder to make maybe the mechanical mode or any support the growing and also the performance impact on the package. So here is the Zemax application. So some of the example. So maybe we can design the smartphone lens module, the laser material processing, and also the flash lidar, or the optical heart rate sensor, and maybe the AR system, and the head-up display in the car. So we also can cover the industrial like life science and research, sensor display and autonomy, aerospace and defense, and the consumer electronic. Okay, here is the summary about the presentation today. So first is about Cybernet Group, as I introduced the Cybernet Group in advance. So we support the customer in the Southeast Asia region, and we are the channel partner of the Ansys in Southeast Asia region. And our service, including the engineering service, training, and the running service, and also the technical support service for like the consultation. So second is the demonstration just now. I demonstrate the double gauge lens design, optimize, and also the straight line analysis. And lastly is the introduction, discuss about the Zemax product and also the product suite. Okay, so this is the end of my presentation.